8.3 Control Quality. Control quality is a process of monitoring and recording results of executing the quality management activities in order to assess performance and ensure the project outputs are complete, correct and meet customer expectations. The key benefit of this process is verifying the project deliverables and work meet the requirements specified by key stakeholders for final acceptance. The control quality process determines if the project outputs do what they were intended to do. These outputs need to comply with all applicable standards, requirements, regulations and specifications. This process is performed throughout the project, and that's from the PMBOK Guide, page 298. The control quality process is performed to measure the completeness, compliance and fitness for use of a product or service prior to user acceptance and final delivery. The control quality process is concerned largely with checking attributes of the product or service being produced, which means the physical properties, and ensuring that they match the scope within tolerances if any. The tests may be destructive, i.e. they may involve bending, stretching, twisting, burning, immersing in water, attacking with chemicals, using at a voltage or current beyond what they're designed for, and measurements recorded at the point at which they failed. Obviously only a sample will be subjected to destructive tests, otherwise nothing would ever actually be sent to the customer. And deciding if destructive tests can be carried out depends on the project. Automobile manufacturers will deliberately crash a number of vehicles when developing a car, but if the project is intended to build just one vehicle or just a few vehicles, it would be totally unacceptable to build one just to destroy it. In this case, some components may be destructively tested and the entire vehicle may be subjected to a virtual destructive test using computer simulation. Most tests are non-destructive because they merely involve measuring, counting, weighing and so on. Other sets of tests may involve bending, stretching, twisting, burning, immersed in water, attacking with chemicals, using a voltage or current beyond what they were designed. But in this case, all of the tests will be kept within limits. So instead of finding a point which it fails, they're proving that the product will still function within its design parameters and be undamaged. For example, I managed an information technology project for a large organization which was intended to develop an electronic form system. The forms could be for any corporate purpose such as invoices, receipts, requests for information, requests for bid, a full range of HR purposes including leave requests, expense claims, overtime requests and so on and so on. The forms would be automatically workflowed around the organisation to be authorised or rejected, placed on hold and whatever, and then automatically filed into the records management system. According to the scope statement, the system would need to be able to handle at least 120 electronic forms per hour. Of the 120 forms per hour, 60% were expected to have an attachment, and the maximum size of the attachment would be 120 kilobytes. When we performed a quality control test, we used a software package to test it automatically. We tested 120 forms per hour. 72 forms had a 122 kilobyte attachment. We ran the test for 12 hours and confirmed that it passed the test. But we were concerned that now that we had a good system, more people would want to use it. So we tested 300 forms per hour. All forms had a 120 kilobyte attachment. We ran the test for 12 hours and confirmed to pass the test. Then we were concerned that holiday periods or unusual circumstances may cause a spike in usage. So then we tested 1,000 forms per hour. All forms had a 500 kilobyte attachment. We ran the test for 12 hours and confirmed to pass the test. The first test proved that the system met the quality requirements. The final test shows it would still be working in 10 years, even if the organisation grows massively in that time. We could have kept on ramping up the test to find the point at which it would fail, but it already proved it was well over its requirements, and so this would have achieved nothing more. This is done by measuring all steps, attributes and variables used to verify conformance or compliance to the specification stated during the planning stage. Of course, we didn't wait to the very end of the project to test everything. Trying to go all or nothing will fail every time. We performed quality control checks on components of the system right through the project, and we did quality control checks of the whole system several times, some of which failed before this final test. Quality control should be performed throughout the project to formally demonstrate with reliable data that the sponsors and our customers' acceptance criteria have been met. That's according to the PMBOK guide. This was an agile project, and so that means that everybody in the team was performing tests. But if we had been using a traditional waterfall method, we would have dedicated a small team at specific milestones or at a project or phase. And by phase I mean a mini project within a main project. In our electronics project, for example, one phase was intended to create an automatic workflow system. Quality control inputs. Number 1, project management plan. The project management plan provides a quality requirements plan which provides how quality control will be performed throughout the project. Input number 2, project documents. The project uses a range of project documents, but they are not considered part of the project management plan. Project documents that can be considered as inputs to this process include the lessons learned register. This focuses on improving quality control and avoiding pitfalls. If you come up with a great idea for improving quality control, or if you discover some traps, make sure you record them to help others on future projects. As they keep saying, don't wait until the end of the project because they won't get recorded or they'll be recorded wrongly. Quality metrics. A quality metric specifically describes a project, the product, attribute and how the control quality process will verify compliance to it. They could be length, weight, thickness, hardness, delay time, frequency or any other attribute. Test and evaluation documents. These are used to evaluate achievements of the quality objectives. Input number 3, approved change requests. A change request submitted to the Perform Integrated Change Control process may or may not be approved. The result of the application is recorded in the change log. It's important to check that the approved changes have been reflected in the scope and quality requirements and that rejected changes haven't been. I've worked in projects where stakeholders believed that submitting a change request would mean it was automatically implemented. Then they'd complain that the product didn't match the scope. And I've worked on projects where the team members thought that scope is set in stone and didn't realise it can be changed through change control. Approved change requests may include modifications such as defect repairs, revised work methods and revised schedules. The implementation of approved change requests should be verified, confirmed for completeness, retested and certified as correct. It doesn't matter how small a change is, it must be tested and re-verified. In the information technology industry, my blood runs cold when I hear programmers saying it's just a one-line change, it doesn't need testing. About 20 years ago in the US, more than 50% of AT&T's network crashed. 75 million calls could not be answered during the next 9 hours. The newspapers are screaming about hackers attacking the system, but the source of all this chaos was eventually traced to a non-tested change in a single line of code in one program. The change caused an electric switch to reset. This sent messages to other switches, causing them to reset, and they sent messages to other switches, bringing down the entire system in domino style. It doesn't matter how small a change, it must be tested and re-verified. Input number 4, deliverables. A deliverable is any unique and verifiable product, result or capability to perform a service that is required to be produced to complete a process, phase or project. Deliverables that are outputs from the direct and managed project work process are inspected and compared to the acceptance criteria defined in the project scope statement. This is a useful definition to remember for the exam. Input number 5, work performance data. Data. Data is raw material that is formatted by reports to produce information. The data we're talking about here are the measurements of technical specifications and observations. For example, the metal plate began to warp when the temperature exceeded 180 degrees Celsius. Input number 6, enterprise environmental factors. These could include project management information systems. Quality management software can be used to track errors and variations in processes or deliverables. Government agency regulations and rules, standards and guidelines specific to the application area. Input number 7, organizational process, include quality standards and policies, quality templates, for example check sheets, checklists, etc., issue and defect reporting procedures and communication policies. Control quality tools and techniques. Number 1, data gathering. And techniques that can be used for this process include checklists. These are very useful for ensuring that everything is checked and nothing is missed. Another benefit is that sometimes there's a specific order for checking. For example, the product may need to be partially dismantled for the test, and so the list can be arranged in that order. The checklist will have provision for recording comments on the results of each test. A checklist is not always a list of conditions and attributes to check. It can also be in the form of a diagram of the final product with tick boxes and areas for comments in each component. Check sheets. These are also known as tally sheets and are used to group similar defects together to make it easier to spot potential quality problems. For an example of this, see figure 8.12 from the PMBOK guide. Statistical sampling. With large numbers of products, it is usually impossible to test them all. And in fact, if you were trying to test them all, then either your quality assurance system has serious issues or you do. You need to test a sample instead, but if you test the first 10 of each 1,000, you may be actually testing items from an individual batch or an individual machine, and so that's not representative of the whole products. If you have a similar problem if you test items at fixed intervals, such as each 10th. To get a representative sample, you need to choose the items randomly. Calculating a truly random number is actually an extremely difficult task, as many systems are biased. That is, there is a hidden sequence underlying them, but even pseudo-random numbers are usually close enough. Questionnaires and surveys. These can be used to gather data about customer satisfaction after the deployment of the product or service. Many people use these terms questionnaire and survey interchangeably, but they're not the same, and in the examination you need to know the difference. So for the exam, a questionnaire contains a set of predetermined questions to be answered, and a survey is the process of analysing the data from the returned questionnaires to produce knowledge. Or to put it another way, imagine we have a customer satisfaction process. The input is questionnaire results, the tools and techniques is the survey, and the output is knowledge of customer satisfaction. The cost regarding defects identified in the surveys may be considered external failure costs to the cost of quality model and have an extensive cost implication for the organisation. Tools and techniques number 2, data analysis, which would include performance reviews. After you have taken measurements of actual results, performance reviews compare and analyse them against a quality matrix defined by the planned quality management process. And this is performance of the system, not performance of members of the project team. Root cause analysis, sometimes called RCA, is used to identify the source of defects. The most common tool for this is the fishbone diagram, also known as the Ishikawa diagram, or cause and effect diagram, or YY diagram. Tools and technique number 3, inspection. An inspection is the examination of a work product to determine if it conforms to documented standards. The results of inspections generally include measurements that may be conducted at any level. The results of a single activity can be inspected, or the final product of the project can be inspected. Inspections may be called reviews, peer reviews, audits or walkthroughs. That's from that's from the PMBOK guide, page 303. Tools and techniques number 4, testing product evaluations. Testing is where you are physically checking the attributes of a product. Unlike the random sampling in a statistical sampling, this is a step-by-step, organised and scripted procedure based firmly on the project requirements, often carried out by experts or at least people with sufficient knowledge and specific training to reliably perform the test. Think of testing a car. You're sitting in the driver's seat with doors and windows closed. The park brake is engaged. You're holding the ignition key. 1. The seat should feel stable and comfortable. Your view should be unobstructed. Report any errors. 2. Insert the key in the ignition. The key should slide easily into the ignition lock. Report any errors. 3. Press the accelerator. Nothing should happen. Report any errors. 4. Put the car in drive and switch on the ignition. The seatbelt warning should chime 5 times at 68 decibels, and the seatbelt warning light on the dashboard should flash in time with the alarm. Report any errors. 5. Fasten the seatbelt. It should be comfortable, not loose. The seatbelt warning line on the dashboard should extinguish. Report any errors. 6. Check the dashboard display against a picture of how it should look. Report any errors. 7. Rotate the ignition key clockwise 1/4 turn. The key should stop turning. The transmission not engaged warning light should display on the dashboard. The engine should not start. Release the key. It should return to its initial position. The transmission not engaged warning light on the dashboard should extinguish. Report any errors. Warning: if the engine starts in test 7, stop the engine, abandon all testing and report your findings. 8. Shift the transmission lever to park. It should remain in its position. Report any errors. 9. Rotate the ignition key clockwise 1/4 turn. The engine should start. All lights in the dashboard should extinguish except the park brake light. Report any errors. And so on. And so on. A step-by-step structured test, and each step the test knows exactly what should happen and is given the opportunity to report variations, errors, defects, bugs or non-conformances, and there are safety precautions built in as well. Now, I'm not a car tester, I just made up that list, so I've left something out or done something wrong. You have to forgive me, it's just an example. The type, amount and extent of tests needed to evaluate each requirement are part of the project quality plan and depend on the nature of the project, time, budget and other constraints. If the project has been to build this car, then all the components of it would have been checked along the way. Finding problems early in the project is a much lower cost option than finding them later. Obviously the actual tests and testing procedures will be dependent upon the project, product and application area. For example, tests required for a car will be different from those for testing a computer program or for testing a house. Tools and technique number 5, data representation. Techniques that could be used for this process include cause and effect diagrams. These are used to identify the possible effects of quality defects and errors. The most common tool for this, you should know by now, is the fishbone diagram, also known as Ishikawa diagram or cause and effect diagram or YY diagram. Control charts. These are used to determine if a process is stable or has predictable performance. Upper and lower specification limits are based on the requirements and calculated using standard statistical calculations. They show the maximum and minimum values allowed. The project manager and appropriate stakeholders may use the statistically calculated control limits to identify the points at which corrective action may be taken to prevent performance that remains outside the control limits. Control charts may be used to monitor various types of output variables, although used most frequently to track repetitive activities required for producing manufactured lots. Control charts may also be used to monitor cost and schedule variances volume, frequency of scope changes or other management results to help determine if the project management processes are in control. Histograms. These are bar charts that can show the number of defects by source or component. The Pareto chart is the most common way for determining the 20% of the sources which cause 80% of the problems. It is based on the 80-20 rule. Scatter diagrams. They show planned variance on one axis and the actual performance on the second axis to see at a glance if the overall state of the product performance. Tool and technique number 6, meetings. The following meetings may be used as part of the control quality process. Approved change request review. This is to check that change requests and approved changes haven't fallen through the cracks. Use this process periodically to ensure that all approved changes have been or are in the process of being properly implemented, tested, completed and certified, and no rejected requests have been approved. Retrospectives or lessons learned, a meeting held by a project team to discuss successful elements in the project phase, what could be improved, what to incorporate in the ongoing project and what in future projects, and what to add to the organizational process assets. Quality control outputs number 1, quality control measures. These are the documented results of control quality activities and formatted and stored as specified in the quality management plan. Output number 2, verify deliverables. A goal of the control quality process is to determine the correctness of the deliverables compared to specification and verify them before they are passed to the customer for acceptance, where they will be an input to the validate scope process. Output number 3, work performance information. The work performance information includes the following information on the deliverables: causes for rejections, rework required, recommendations for corrective actions, list of verified deliverables, status of the quality metrics, and need for process adjustments. Output number 4, change requests. The quality control procedure is not a good, bad or black-white selector. There are shades of grey. As we saw with the work performance information, where there are requests for rework, corrective actions, process adjustments, which could be part of preventative actions. All these changes require the project manager to submit a change request, which will be processed through the Perform Integrated Change Control process. Output number 5, project management plan updates. Any change to the project management plan goes through the organization's change control process via a change request. In this process, the components that may require a change request for the project management plan is the quality management plan. Output number 6, project document updates. The documents that may be updated as a result of carrying out this process include the issue log. Many times the deliverable that does not meet the quality requirements is documented as an issue. This is particularly true if a number of products represent with the same or similar fault. Lessons learned register. The register is updated with information on the source of the quality defects and how they could have been avoided, as well as approaches that work well. You might remember the check sheets I mentioned earlier in this lesson. These are also known as tally sheets, and they're used to group similar defects together to make it easier to spot potential quality problems. You might find that many of the items have paint runs and sagging, which can indicate a spray plant is too much paint, the spray head moving too slowly, or other faults. Risk register. New risks identified during the process are recorded in the risk register and managed during the risk management process. Test and evaluation documents. These may be modified as a result of this process in order to make future tests more effective. The modifications could also be recorded in lessons learned with a follow-up comment on how effective they were. Well, that brings us to the end of control quality and also to the end of the project quality management module. Although there were only 3 processes, I'm sure you'd agree that there was a lot of information packed into it. The next module is Project Resource Management, and the first lesson is 9.1 Planned Resource Management. Please read the corresponding chapter of the PMBOK guide before watching the video. Now, if you're familiar with previous editions of the PMBOK guide and you've never heard of Project Resource Management before, it's because previously it was called Project Human Resource Management, and it's been that way for all versions of the PMBOK guide until the 6th edition.